Hi students, how are you? I think it's fine. Myself, Tanmoy Dotto, Assistant Professor, Department of Chemistry, JS College of Engineering, Kolani, welcome you all in my class of hybridization. You know, what is the hybridization? Hybridization means here we will discuss about the that how many orbitals, atomic orbitals are involved when one covalent bond or when one covalent molecule is formed. That means how many orbitals are involved here. For example, if we think about the most common covalent compound, that is the CH4. So here we will discuss here, or the question may be asked in this way, that what is the hybridization of carbon atom? What is the hybridization of the carbon atom? So then you have to understand that how many orbitals are involved to form the methane compound. Okay, and another thing, very important thing which you have to keep in mind, that hybridization, this is only applicable for covalent compound. This is only applicable for covalent compound. It is not applicable for the ionic compound. So for covalent compound, or what we'll discuss in the hybridization chapter, here all the discussion depends on the covalent compound or the such kind of things. So how we can understand how many orbitals are involved? Because if you think about the carbon and hydrogen, there are some orbitals are involved for carbon and some orbitals are hydrogen. So finally there may be one s orbital, two p orbital, there may be one s orbital, 3p orbital. So in this way we will discuss that how many orbitals are involved here. So if there one s orbital and one p orbitals are involved, then we call the hybridization of the central atom is the sp. But if in the compound one s orbital and two p orbitals are involved, then we call this is the sp2. But if the in the compound 1s and 3p orbitals are involved, you know, in the p there are three orbitals, and generally we write down here in this way. So one is the px, as you know, another is the py, and another pz. So px, py, and the pz. So then we call this is the sp3. So in this way, if there is any contribution of the d orbital, then what happen? If there is any contribution of the d orbitals, then we can write down that for example here 1 is there 3p and 1d. Then what happened? The hybridization will be here. The hybridization will be here sp3d. If in the compound that two d orbitals are involved, 1s, 3p, and 2d, then the hybridization will be sp3d2. So in this way we have to find out the hybridization. Now how we can find out the hybridization, I will discuss at first the theory, then there are some rules also by which easily we can determine hybridization, because the structure, the shape of the compound, okay, the shape of the compound or the geometry of the compound also depends on this hybridization. These are very much depends on the hybridization. Okay, so first of all, if we take the very common example, that is the methane, for example, very common example, CH4, methane. So if we take the example methane, then we can write down there C plus H plus H plus H plus H, you know, isn't it? Now what is the atomic number of the carbon? What is the atomic number of the carbon? The atomic number of the carbon is the 6. So if the atomic number of the carbon is the 6, then we can write down the electronic configuration in this way. This is the 1s2, 2s2, 2p4. Now you have to keep in mind that what we are doing here in the case of the hybridization, that all the things depends on the valence electronic configuration. That means here we have to concentrate only 2s2 2p4. Okay, there is no requirement of the 1s2. So it is applicable not only for this case, each and every case you have to concentrate only the valence electronic configuration. Okay, this is the valence electronic configuration, so we have to keep in mind each and every case. So 2s2 2p4 is our important fact here. Now if you think about the 2s2 2p4, then here look here that if I draw the shape of the if we draw the electronic configuration, then for carbon, look here, it is the 2s and it is the 2p. So you know 2s2, so we can write down here 2s2 in this way, that it is the 2s2 and 2p4. So sorry, it is a 2s2 2p2, not 2p4. It is the 2, because the electronic configuration of the carbon is 6, so it is the 1s2 2s2 and 2p2. Okay, so that's why it is total 6, so 2p2, so it is the 2p2 in this way. Okay, now how many electrons are required for the carbon to get the configuration of the neon? So obviously answer will be 4, isn't it? Because if there is 4 electron, then only 4 plus 2 6, or 6 plus 2 8. That means 4 deficient electrons are there for the carbon. If you think about the carbon, then it is the number of electrons is the 6. So what is the requirement? Requirement is it is actually 2 plus 4. That means to get the 8 electronic configuration, 4 electrons are required. So 4 deficient electrons are there. So if there are 4 deficient electrons are there, obviously this is the covalent compound, then you have to keep in mind that there must be sharing of the 4 electrons. So here we can write down, in case of carbon, look here, if you think about the carbon, then there, what I told you, that here 2 electrons and here 2 electrons. Okay, so now 4 hydrogens are there. Okay, 4 hydrogens are there in case of CH4. 4 hydrogens are there. If you think about the 4 hydrogens, then each and every hydrogen if share one electron, then overall carbon will get the 4 electrons. That means carbon will get the configuration of the neon, that is the nearest inert gas electronic configuration, neon. Okay, so that means 4 hydrogen should share the each and every electrons here. So how is it possible? Is it possible because 4 half filled orbitals are required, so 1 electron should jump here. So that means in the excited state the electronic configuration will be like this. Electronic configuration will be like this in the excited state, that it will be 4 half filled areas should be available. 1, then 2, then 3, 4. Okay, so 4 half filled orbitals are there. Now look here, 1 by 1 hydrogen will share 1 electron. 1 by 1 hydrogen will share 1 electron. 1 by 1 hydrogen will share 1 electron. So that means 4 covalent bonds are formed here. Okay, so look, for each and every case there are 4 covalent bonds are formed. And what is the hybridization? Look here, the contribution of the orbitals. Here it is the s, 1s, and it is the 1p, suppose px, py, pz. So there are 3p orbitals, so hybridization will be sp3. And you have to keep in mind the geometry of the sp3. It will be tetrahedral. The geometry will be tetrahedral, and the tetrahedral looks like this way: C H H and H. So these are the 4 bonds, okay, and this is the tetrahedral structure. This is the tetrahedral structure, and obviously this tetrahedral structure has the hybridization sp3. Okay, so in this way we can determine the geometry and the hybridization of the compound or a particular compound, but not each and every case. This is the octet fill-up. Okay, so octet fill-up means there should be inert gas configuration. So octet fulfill is not happen each and every case. There are some exceptions also where you will find out that there is no such kind of cases of octet fill up. So if you take the examples of the most common example is the BF3. If you take the example of the BF3 is very stable compound, but here octet fill-up is not happen. Like if you think about the electronic configuration of the boron, then valence electronic configuration, then it looks like in this case like here is the 1 electron and here is the another electron. So boron, carbon, here is the 2 electron and here is the 1 electron. So it is the electronic configuration. So if you think about BF3, then there will be 3 F atom. So F also required also shared to 1 electron, then it will get the configuration of the neon, and so that's why 3 half filled area is very much required. So just transfer 1 electron here. So then what happened, then here you can see that it will be looks like this way, and there are 3 fluorine atoms are there, and hence here it is the 1 fluorine, it is the another fluorine. Okay, so in this way it is the BF3, and hybridization 1s is there and 2p is there because this is the vacant, so no responsibility of the hybridization. So you have to keep in mind one thing: if any of the vacant, I will show you one example also, that any of the fulfilled orbital is present in the inner side, you have to consider for the hybridization. If it is the inner side, consider, but if it is the outer side, it should not consider, okay, it should not be considered. Okay, so here the hybridization, what is the hybridization? The hybridization of the compound is obviously it will be the sp2. And what is the structure or the shape of the geometry of the sp2? The geometry of the sp2 is here. It looks like triangular. Okay, so the geometry of the sp2, it is the triangular. So if it is the in the middle, there is B, it is the F, it is the another F, and it is the another F. So it is the BF3, and the name of the structure is the triangular. Now come to the fact another type of examples, and this is the this is the another type of example. Why it is another type of example? Like H2O. If you taking the example of H2O, okay, so if it is the H2O, then in case of O, in case of oxygen, here you know what is the electronic configuration of oxygen. So here electronic configuration is oxygen is here, that it is 1 2 3 4 5 and 6. So two half filled orbitals are also there, so that means two electrons should share here, and already there are two hydrogens are also present, because if H2O, then it will be O plus 2H. Each and every hydrogen, you know, it share one electron. So what happened actually here, one hydrogen, here another hydrogen. Okay, so in this way, look here, that the what is the hybridization of the compound H2O. What I told you in the previous case, that hybridization, you have to consider the inner orbital. So it is the inner orbital. So here you have to consider, because this acts as a lone pair. This acts as a lone pair. Same case for this one also, but the hybridization will be S plus 3p. That means the hybridization will be sp3. Okay, but there are two lone pairs. When there is a question of the lone pairs, their original geometry, okay, geometry will be tetrahedral. I will tell you that what will be the geometry for each and every case. Geometry will be tetrahedral. It is the tetrahedral. Okay, no problem about this, but what will be the shape of the molecules? Shape means when their lone pair should not be considered. So first of all, I'm drawing the shape of the H2O. Then it is the oxygen, and there will be two lone pairs will be there. It is the one lone pair, and it is the another lone pair. Then here one hydrogen, here another hydrogen, here two lone pairs are there. Okay, and two lone pair means here it is the one lone pair for this one, another lone pair for this one, and two bonds are already there. So two bonds are already available here. So it is it originally it is the tetrahedral, but when I'm considering the shape, then you have to omit the lone pairs. Okay, you have to omit the lone pair. So without lone pair, look, the structure is looked like a V, isn't it? So this is called, the shape of the molecule is called actually a V shaped. It is the V shaped. So first of all, you have to know what is the geometry of each and every corresponding hybridization. So I will show you that what will be the geometry for each and every case. First of all, if the hybridization is like sp, it the shape will be linear. It will be linear. For example, there are so many examples like BeF2, like BeF2, like BeCl2. Okay, so it looks like BeF and F. So this is the shape of the molecule. Okay, and it is actually the linear. But if the hybridization is like, if the hybridization is sp2, then it will be triangular. For example, if you take the example of BF3, what I already discussed, so it looks like triangular. Now if you take the examples of the sp3, what I already discussed with you, sp3 general geometry tetrahedral if there is no lone pair. And for example, most common example here, like of sp3, like methane. Okay, if it is the sp3, if it is the sp3d, then it is the geometry will be the TBP. That means trigonal bipyramidal. For example, the most common example of the TBP structure is the PF5. It is the most common example, PF5. So how it looks like? It looks like, actually the TBP structure looks like, this is the plane, Okay, so in this plane there are three molecules are there. Central atom one will be central like pf5. So here and the upper side will be one bond and lower side will be another bond. Okay, so what the molecules will be like, here it is the p and there are also three bonds. Okay, and all the atoms are here, like it is the f f f f and f. So this one is the upper side of the from the plane. This fluorine is the upper side from the plane, it is the up side, and this is the below side of the plane, and this is the plane actually. This one is the plane. Okay, so this structure is called, or this hybridization, corresponding hybridization is called actually trigonal bipyramidal structure. Now if it is the sp3d2, sp3d2, then the name of the structure is the octahedral. It is the octahedral. For example, SF6, the most common example, sorry, SF6, the most common example of SF6. This looks like, how it looks like, it looks like that here it is in one plane, it is the plane actually, and in this plane there will be one upside atom, it is the upside atom, and another is the below side. Okay, and in the center, obviously in the center there will be central atom sulfur, and from the central atom all the other atoms are like this. Okay, so this looks like octahedral, and this one is the upper side and this one is the below side. Okay, and the next one is the sp3d3. okay, the name of the structure here, the name of the structure is, it is called pentagonal bipyramidal. The name of the structure is called pentagonal bipyramidal, and it looks like, it is the pentagon almost. Okay, it is the pentagon, and in this pentagon there will be one upside atom, another downside atom. Okay, so this is the upside atom, another is the downside atom, and in the center, obviously, for example, here I will take one example of the pentagonal bipyramidal, and example is the IF7. okay, so here for example, here in the central part here will be I, and all the 7 atoms are like in this case, in this way, and this is called the pentagonal bipyramidal. Okay, so now I will show you another thing which is very much important, that for example, I will show you one structure of the compound, like SO2. Okay, SO2. okay, so for SO2 here, look here, sulfur plus 2 oxygen. Okay, but oxygen, there is an important case. When oxygen acts as a side atom, then what happened? It formed 2 bonds. Why 2 bonds? I will explain. 2 bonds. Why? Because it has the 6 electrons, so 6 electrons, so 2 electrons are required. 2 electrons are required for the inert gas configuration, and that's why oxygen will form 1 sigma plus 1 pi. oxygen will form one sigma and one pi bond. Okay, because if with sharing the one electrons, one bond each formation will occur. If there is one electron is required, then after sharing one electron, then what happen, it can get one electron. So if it is two electrons are required, there must be double bond. Double bond means one sigma bond and second one is the pi bond. Okay, sigma bond means it is the direct overlap. Okay, this type of overlap. And pi bond means, what is the pi bond? Pi bond means it is the side by side overlap. It is the this kind of overlap will be there. Okay, so whatever, this is not important here. You have to know for any such kind of atom which is not monovalent, it is the bivalent actually, because two deficient electrons are there. So I'll give you one example like SO2. If you think about the SO2, then sulfur, here sulfur, then outermost electronic configuration of the sulfur is here, like it is the, so this is the outermost electronic configuration. But look here, for one oxygen, if one oxygen, two electrons are required, two bonds will form, then two half fill orbitals are there. So for two oxygen there will be four half fill orbitals are there. So that means there must be four half filled orbitals are required, but here only two half filled orbitals are available. So another one orbital is very much important, very much required. So you know sulfur has the d orbitals also, isn't it? Sulfur has the d orbitals. So if sulfur has the d orbitals, vacant d orbitals, then what happen? Sulfur can use that d orbitals for the bonding purpose. So in this way, one electron of the sulfur, it can transfer here to here. So ultimately what happened after transferring, what happened? So here electronic configuration will be like this. Here 1 1 1 1, and here in the d orbital, look here, here will be one electron, and that remain the same. So now if there are two oxygen, each and every oxygen will form one sigma, one pi, then what happen? Here it is the one oxygen which forms sigma bond and one pi bond also, it is the another oxygen, so expected another oxygen will form here, it is the sigma and pi. So you have to keep in mind, when you are considering the hybridization, just keep in mind, ignore the pi bonds. That means here, look here, that two pi bonds are there, two pi bonds are formed here. One is this pi bond, another is the pi bond. So we'll not consider during the hybridization, just forget about these two pi bonds. We'll consider only this one and the inner one. That means 1s and 2p. So its hybridization is the sp2. Don't write down sp3d, because these two are pi bonds, so forget about the pi bonds. Where pi bond is formed, will not consider in the hybridization time. So its hybridization 1s and 2p orbitals are there, so sp2. In this way we can determine the hybridization when mainly oxygen is present. Where oxygen is present, in this way we can determine the hybridization. So now this is the basic theory regarding how we can determine the hybridization. But there is some rule, I told you, there is a rule by which we can determine easily the hybridization of any of the molecule instant. Okay, that means this is the basic theory how we can determine. But other than this, we can determine by the hybridization that H equals to, then in a rule, H equals to V plus generally V plus X minus C plus A. I'll tell you what is the V, what is the X, C and A. Just listen carefully. That V means it is the valence electron of central atom. valence electron of central atom. Okay, what is the X? X is the number of monovalent atom. Monovalent, keep in mind, monovalent atom. Oxygen not a monovalent atom. Okay, only if their monovalent atoms are there we have to consider. C, cationic charge, it is the cationic charge. And A, of the compound, obviously of the compound, it is the anionic charge. Okay, so by following this equation, if you get any of the value, then you can determine from here the hybridization. I will show you one example. For example, if you think about the SO2, just what we discussed here, SO2. In SO2, look here, in SO2, if you think about the SO2, then H equals to half. What is the valence electron of sulfur? The valence electron of sulfur is the 6 plus X, monovalent atom, no monovalent atom, so it will be 0. No cationic charge, no anionic charge, so it will be 3. 3 means sp2. Total number of orbitals will be 3. Okay, total number of orbitals will be 3. Here if you get the value of 2, it will be sp. Here if you get the value of the 4, then it will be sp3. 3p orbital, 1 s orbital. Okay, so if you get the value of 5, then it will be sp3d. Number of orbitals you will get from here. Okay, I'll give you another example. If you take the example of NH3, then H equals to half. What is the valence electrons of nitrogen? It will be 5 plus 3 minus 0, no cationic charge, no anionic charge, so it will be 4 means sp3d. So by this way you can also determine the it will be sp3, no, there will be no d because it is the 4, so obviously it will be only sp3. So hybridization of NH3 is the sp3. So by this way you can easily calculate what will be the hybridization of the central atom. Okay, it is the easiest way by which you can do, or you have to do. So now I will give you some examples also. You have to do in your home by this method, or you can check also, cross check also that either it is right or wrong by the VVT method or the previous method actually. So just write down, it is the home task you have to do, that you have to find out the hybridization. Okay, for example, like write down XeF2. Okay, like I3 minus like SF6, like BrF5, IF5, then XeOF4. So these are the home tasks which you have to do. Now there is another thing which you have to know, or which you have to understand, which is very important, that is the hydrogen bonding. Okay, or coordinate covalent bonding. Till now what we discussed, it is the covalent bond, it is the generally the covalent bond. But when coordinate covalent bond will be formed, like if you think the example of the coordinate covalent bond, like there is a compound of NH3, the very basic compound NH3, that 2 electrons will donated to BF3. Okay, like if you think about the BF3, I already discussed in the compound of BF3 what is the hybridization. The hybridization looks like in this way. Okay, so here it is the 1 1 1 and 3, here 3F formed covalent bond. So then nitrogen, you know already lone pair, nitrogen has the lone pair. Okay, so this nitrogen 2 electrons can share here. So by this way, look here, boron, its octet fill up occur, okay, because there is a vacant site also available. This vacant site will be fulfilled by the NH3, and also NH3 donate its lone pair. So that means it looks like NH3 its lone pair giving the arrow mark to BF3. So this is basically called coordinate covalent bond. Coordinate covalent bond means coordinate covalent bonds. Coordinate covalent bond means there one compound will donate, or one atom will donate the 2 electrons. Okay, then no sharing of the occur. Sharing, but after donation, one sigma bond or one pi bond, whatever, one covalent bond means there are 2 electrons. So after formation of the compound, it is very difficult to understand that which atom will which atom donate the electron to which atom. But during the formation time, one electron will not come from each and every atom or the compound. It will be the totally donated by the one compound or one atom to another compound or the atom. Okay, this is called the coordinate covalent bond. And another type is the hydrogen bonding. This is the weak interaction, okay, which present in various type of compounds, and this is very much helpful to explain various kinds of parameters, factors by this hydrogen bonding. So hydrogen, it form a weak bond with the 3 atoms, okay, like oxygen, mainly oxygen, fluorine and nitrogen. Okay, when hydrogen again it is attached with another electronegative atom like fluorine, oxygen or nitrogen. So this kind of interaction is called actually hydrogen bond. This kind of interaction is called hydrogen bond. So what is the hydrogen bond? Hydrogen, when it attached with very electronegative atom, then it form a weak interaction with mainly oxygen, fluorine and neon, some case Cl also, chlorine also. This kind of bond is called actually hydrogen bond. Okay, so that's all for today. You have to find out what is the hybridization of the compound, and there are different kinds of problems are also available regarding the hydrogen bonding. You have to check all these things. Okay, thank you. Meet with you in the next class with a different topic.